The first slide, I would like to acknowledge a lot of collaborators. I mean, I will be talking about things we have been understanding over 10 years, so there's lots of names. For the talk of today in particular, I would like to acknowledge Marino Arroyo from Barcelona, Alfred Beran from, he's a biologist from Trieste, Giancarlo Cicconofri, a former student of mine, and Giovanni Noselli, a collaborator in Trieste. So, I mean, I am part of a workshop that is also celebrating women in material science, and I felt I wanted to contribute, even though I'm not listed as that. So it's a very difficult topic, and especially delicate since I'm not a woman, but I decided to do it nevertheless. And in this, I gave me some rules. I mean, it turned out to be much more difficult than I thought. And so the rules I gave, I gave myself some rules. And so the rules was to exploit the history of Cambridge, this wonderful city where I'm often a visitor, which is so full of scientific heritage. And in fact, I restricted furthermore the scope and only using trees in Cambridge. And so you may have noticed that there's a tree just here. And those of you who are still in contact with nature will have noticed that it's an apple tree. And obviously, the connection between apple and the Newton Institute is obvious, right? I don't know whether you noticed that, but yes, it's not by chance. And maybe I'll tell you some more later. And so then I discovered that not far away from here, there's another tree. At the Newnham College, which is down the road, you can go there, it's 5 minutes walking from here, there is a tree called the tipper tree. Now, tipper is not a fruit. So the tipper tree was planted on the 6th of February of 1994 to celebrate the 100th anniversary of Constance F. Tipper, née Elam, who died in 95, 101 years old. So she was an English metallurgist and crystallographer, educated at Newnham College. In 1923, she received the Royal Society Beckerian Medal for groundbreaking work on crystal plasticity done together with G.I. Taylor. Now, G.I. Taylor is very well known to many of you in the audience. You can see a portrait of G.I. Taylor if you go to the cafeteria here at DAMT and you look on the left while you're ordering your sandwiches, you'll see a portrait of G.I. Taylor. She did the first scanning electron microscopy of fractured surfaces in metal using one of the first SEM ever built by Charles Oatley. I've been a visitor at the engineering Department of Engineering in Cambridge for 1 year, sitting in the Oatley labs. And she got the Thomas Lowe Gray Prize for a paper joint with Baker. Now, the Oatley lab sit in the Baker building of in Trumpington Street. It's the beautiful 1953 building over there. And so this was in recognition of paper, the value of the notch tensile test to assess the brittleness of fracture in steel, which is known as the Tipper test. And other department colleagues of fracture fame, I mean, it's one of the treasures, or if you want, the legacies of that department to have developed fracture mechanics. I mean, Griffiths, the Griffiths criterion, which is made even to math audiences. It's a very vibrant area of research in math PDEs right now. In Inglis, there's another building dedicated to Inglis. And so I was really shocked. I lived for 1 year in the Baker building, next to Inglis building, etc. I never heard the name of Constance Tipper. I have two anecdotes. One is related to the 1923 Royal Society Medal. So it was a tradition that the recipient of the medal was invited to a dinner at the Royal Society Dining Club. And this caused a problem because she was not, I mean, there was a gender problem, right? And so there was, you know, glitches, and this is what she wrote to excuse herself from the dinner. I'm sorry to have given you so much trouble. I felt very much honored on receiving your invitation, although I realized that it had to be being sent under a misunderstanding. The second is the tipper test, right? So this is another thing that I was trained as an engineer, right? Everybody who's trained in fracture mechanics knows about the Liberty ships. Now, engineering works by disasters, right? So what are the famous disasters that everybody knows? The Liberty ships, I'll tell you in a second. The Tacoma Bridge, everybody knows about the air elasticity of Tacoma Bridge. The Challenger disaster, right? Now, this is a story that resonates a lot with the Challenger disaster in the sense that the Liberty ships are these ships that were manufactured during World War II in the US, much faster, using welding technology as opposed to rivets. And then it so happened that when they were sailing in the cold waters of the Atlantic, they would crack open. Actually, we can do an experiment. So if you see the pictures of the Liberty ships, they crack like this. You will see pictures of half of a ship cracked in two, right? And so there was, studies on trying to understand what was happening. And so the tipper test was, so this is from the paper so anyway, one of the explanations is the fact that low temperatures change the behavior of steel, of mild steel, from ductile to brittle, okay? And so part of the reason was with the lack of connection between the experiments to assess the material properties that were run at lab temperature and the operating conditions in which the ships were traveling in water at freezing temperature. And so in the abstract of this paper that received the medal, there is the essence of the paper, which is the fact that the designer of orthodox fabricated structures must be provided with material which is ductile at all operating temperatures and stress levels. Now, I could not help resonating this with something that everybody knows. Everybody knows that Feynman was part of the Challenger committee, the NASA-appointed committee to assess the Challenger disaster. And there is this famous thing that he drops an O-ring in a glass of ice water and demonstrates the fact that the O-ring has different properties, rubber has different properties at different temperature, and this could be the cause of the Challenger disaster. And so the thought was, what if had been Feynman, the person invited to that dinner in 1923? Now, Newnham College is here. It's very famous for its alumni. One of them is Rosalind Franklin. I will not even start talking about Rosalind Franklin. Let me talk about the one that is just next to Rosalind Franklin in alphabetic order. It's Philippa Fawcett. In 1890, she scored the highest mark of all candidates for mathematical tripos, another Cambridge legacy. But she was placed above the senior wrangler, that is above the top first, because women were not then eligible for the Cambridge BA degree and therefore could not be classed as wranglers. Now, Rosalind Franklin, everybody knows this, right? Photo 51. Photo 51, how much crucial photo 51 was in the Watson and Crick thing, how much under-acknowledged this was, etc., etc. I recently heard a beautiful interview to Raymond Gosling, the author of this picture, who was telling the reaction of Rosalind Franklin when it was clear that this photo had, made it and, had decided the thing. And she says her reaction was typical of Rosalind. She was not furious. She didn't use the word scooped in the sense she didn't say they stole, But what she actually said is we all stand on each other's shoulders. Right, and so this brings me back to the tipper tree. So trees, this apple tree is a bit ill, so we are worried. I spoke yesterday with the director, David Abrams. So this apple tree comes directly, it's a cutting from a tree that supposedly saw Newton's time, right? And that's why it's here. And so I was worried that the tipper tree could be in poor health, and so I went to see the tipper tree. So the tipper tree is in very good health. You can all see it. This is the tipper tree a couple of days ago. There is no label marking all the story, so in order to learn about the story, you have to do a little bit of research. That's what I had to do, so I had to speak with the college archivist. And so yes, there is no label, but I was told that they are preparing a book or a publication that will be available to the visitors, in which the story of this tree will be available. Okay. Sorry, it took me some time, and now I can talk a little bit about the topic of my talk. So I want to talk about, it's very much in line with the beautiful things that Ivan told us. So I would like to, so our research is motivated by this looking at nature and biology, and in particular very small systems, the way they move, what they do, and engineering, trying to reproduce something which is very far away from what we can reproduce right now. So I'm interested in biological machines. We have heard already something about this, so I will not talk much, but this is a sperm cell. It's a fantastic machine, a cargo containing the precious material, and a propulsive system, a beating tail. It's such an elementary design that we have already seen this. People have tried to reproduce it with a red blood cell, a functionalized magnetic tail that is put into motion by an applied field, and right. And the minute you start doing that, however, you realize that things are much more interesting than what they seem. For example, one of the obvious observations here is that this swimmer is very incompetent for the function that you have thought about, because it's swimming not with the cargo in front, right? But it's swimming with the tail in front. So if it has to deliver something, it will have to rotate at arrival, right? And so you start now immediately asking yourself the question, what controls the direction of the velocity, the sign of the velocity? Can you affect that? Can you control from outside? Do you have a reverse gear or not? Et cetera, et cetera, et cetera. So this is the topic that, okay, so this is the topic I want to investigate. I want to investigate this type of problems, and in particular, the role of body architecture in biology in producing a certain function, so that when you try to reconstruct it, you have a detailed understanding of what is the impact of the architecture on the design, right? So we have heard about this in this conference, two beautiful talks by Monica de la Cruz and Daphne Klotza, so I will not talk a lot about this. And what I want to talk about is the variety of architectures that exist in nature to implement the swimming behavior. So we have talked about this one. Ivan Smaliuk has briefly mentioned this, which is the bacterium flagellum. There is a rotary motor here that moves this guy. But I want to talk about the black and white side of this picture. So this is a family of organisms that is called Euglenids. These are SEM pictures of their cell envelope. So under the plasma membrane, they have an ultrastructure made of proteinaceous strips, which are the things we see here. And so it's obvious that the architecture is interesting. It's visually appealing. I want to ask the question, is it used for a function? How is it used? What can we learn from this picture if we want to do something with it ourselves, in the spirit of Ivan? So this is our pet Euglenid. In fact, this is not even, we have studied Euglena gracilis, and now we study it by cultivating ourselves, thanks to a collaboration with a biologist. But what you see here is a YouTube movie from another species. And you see something with the body with flagella. So this guy can swim by beating flagella exactly like a sperm cell. But in addition to that, and you have already seen that already in this conference, it can do this, okay? So this is a interesting, very, elegant and coordinating motion. You can think of it as like a bulge moving along the body, and the body having this kind of peristaltic waves that, and it's a behavior that involves the body, not the flagellum. So it's clearly a different behavior, right? And so this unicellular organism, it's an organism without a brain, can execute a change of gait, not unlike a horse that walks, trots, gallop, and can choose what is the good gait depending on the speed at which you want to go, okay? I mean, how horses do that, it's another complicated thing, but certainly this guy executes this change of gait without a brain, because it doesn't have a brain. Okay? It's a unicellular organism. And so we were fascinated by this gait switch, and we tried to investigate the how, so how it's executed. How does this organism execute these shape changes, for example, and why? Okay? And this is the whole story. I will only talk about half of the story. So the first half, I talked about it at the previous workshop in this series. There is I mean, another beautiful thing that the Newton Institute does is these incredible videos where you can go back and watch things. So mine would not be incredible, but if you want to know about this story, it's in the archive of the Newton. One thing I should say is that in doing this and in studying the swimming mechanism, we use fluid mechanics, so the interaction of a change of shape with a surrounding fluid, right? So you change shape, the fluid is pushed around. It doesn't like to be pushed around. It exerts a reaction and use that reaction to swim, right? So this is, in two words, the mathematical theory of swimming. And one thing that we discovered is that this beautiful pattern, which are the trajectories, which have a very distinctive shape. They are generalized helices. They're very reminiscent of trajectories of magnetic particles in a magnetic field. No chance, it's exactly that. So we managed to prove within math and hydrodynamics the fact that at low Reynolds number, so without inertia, if there is no inertia, the genetic trajectory of any organism that swims by beating periodically a flagellum over an array of cilia is a generalized helix. Okay? And so there is a little theorem about that. Now, on the right-hand side is my topic for today, is control of your surface, right? How do you control your shape? By doing something to your surface, okay? So the topic here is elasticity. So if you want, it's shell theory, active shells, because the shells have something which have motors, right? And so the story is about the theorem of Gauss, the Gauss theorem. So I will say the conclusion immediately, because it will take me some time to explain how this works. So the conclusion is in this picture. So you see the same organisms in two different shapes, and what you see is that the famous strips that I showed you before in SEM, which you can see here and here, so the way the organism changes shape is through the sliding of these pellicle strips. This sliding is a shear, so it's a change of metric of the surface, and the change of metric causes change of Gaussian curvature, and so the change of the shapes. So the control of the shape of this unicellular organism is done by an exquisite control and knowledge of the Gauss theorem. Okay? And so let's see how this comes about. So if you think of controlling your shape as an engineer, I am an engineer, you are told that there are basically two routes. Actually, you're told only the first one. Okay? And the first one is exploiting through the thickness changes of stretches. And the prototype is the bimetallic thermostat, actually. So you have two metals with two different thermal expansion coefficients. You induce different relaxed states in the two layers, and you produce curvature, because here, the metal that has a greater coefficient of linear expansion wants to expand more, and so it will become the extended part of the shell, right? So there's a formula due to Timoshenko which tells you that you need this delta means difference, right? You need difference across the thickness, and you can do lots of beautiful things with this, even in the soft context, okay? So we did something a few years ago, and Dirk Brouwer has done beautiful things on this. And another Cambridge story, I thank Mark Warner for being in the audience and having taught me this, is that you can become even very rich with this story by building the switches, the thermal switches that govern the behavior of every kettle that is built in this country, to the point that then you can donate a lot of money to the college where you studied, Corpus Christi. You can build a library for the students. You can build a clock, which is here, the chronophage, the Corpus clock, which is one of the greatest tourist attractions of the city now. So this is route A, which makes you very rich. Route B, which is even older, and it's a topic that is old for certain reasons, but it has become part of the contemporary discourse thanks to, let me call it the school of Eran Sharon, so the school in Israel. So we have heard Hillel Aharoni speak about this, and Mark Warner has done many interesting things. This thing is to use the theorem of Gauss. Theorem of Gauss means that you have okay, let's say a sheet, the coordinates in a flat, I have my reference coordinate UV, and then I prescribe a map, okay? A map is this X. I take derivative of this map, scalar products, and I get the metric tensor of the surface, which measures the changes of length and angles of the material fibers in this reference sheet, right? And the contribution of Gauss, K here is the Gaussian curvature, E is this coefficient, is that you can express the Gaussian curvature invented by him as a product of the Christoffel symbols, and the Christoffel symbols can be obtained as derivatives of the metric tensors, okay? So the conclusion of this in the mind of an engineer reading this is that you can control Gaussian curvature by controlling stretching and shears in a surface, right? Everybody knows this. The map maker's problem has been alluded to. Let me do the same thing with the perspective of a mechanical engineer. Mechanical engineers call resistance by shape this phenomenon. Okay, so maybe before I say this, is Sabetta Matsumoto? Yes, Sabetta is in the audience. So one of the consequences of the unstretchability, so this sheet does not stretch well, is the fact that it's very bad. If you dress yourself in paper, it's very bad. Because since the thing does not want to stretch, it cannot have Gaussian curvature, and so it doesn't dress well. So the beautiful thing she talked about, which are stretchy, they use the weaving to stretch, dress much better. So this is one of the... Now, coming from Naples, my take on this is on the pizza eater problem, which is the fact that, so you know this, right? And you can reproduce it with a sheet of paper. So the thing, the paper cannot sustain gravity because it's very soft in bending if you allow it to not to develop Gaussian curvature. But if you pre-bend it in this way, not only it sustains its weight, but it can sustain objects, right? Okay. And so it's resisting by stretching. So if it has to yield to gravity, it has to develop Gaussian curvature, non-zero, starting from a state in which it had zero curvature. It means that this has changed. The right-hand side must have changed. The metric must have changed. The thing must have stretched. Okay, so this sheet of paper resists to bending by stretching. And so this is one element. Another element, so here there are derivatives. So another element is that if you want now to, so this is a basic mechanism that show you that Gaussian curvature, in order to generate Gaussian curvature, you have to generate, I mean, it's subtle. I mean, this works particularly well, but so you could deform the cylinder. My thing is not working. The cylinder on top could deform into a cylinder. So it's made with, okay, experiment. So here is a picture, there is a picture of this object. So I can deform this thing, right? But I can deform a cylinder into a cylinder, and I develop no Gaussian curvature. Instead, this guy here is developing Gaussian curvature, right? Because there is a curvature in this direction and a curvature in this direction, right? So the Gaussian curvature in this guy here comes from a second order subtlety in this formula, which is the fact that not only you are stretching, but you are stretching differentially from the edge where the things are glued to one another by the cutting process, and the center where there is no lateral constraint. Okay, so the Gaussian curvature of this object comes from the fact that the lateral contraction is not allowed here and it's allowed here. Okay? And this generates a Gaussian curvature. So this effect is this derivative comma u here. Okay? Now the reason I'm saying this is because this formula, it's very difficult. It looks very intimidating. I have not written the formula for the Gaussian, for the Christoffel symbols. But if you look at actual implementations of this formula, it can be remarkably simple. And so Euglena uses, in the behavior I showed you, two special facts. One is that it's using shears. So the pellicle slide. So the mechanism, the basic mechanism is the sliding of, of strips. And the second thing that it uses is the fact that it's actuating in an axially symmetric way. Okay, so in this famous map that in principle could depend on u and v, the horizontal u azimuthal coordinate, and v the vertical. Maybe I should explain this picture. So let me explain this picture first, and then I'll go back to there. So in this picture, we are exploiting the fact that if you take a cylinder and you fold it or unfold it, these operations can be done isometrically. You're not changing the metric, right? So we study the behavior of an axisymmetric tube by studying the planar behavior. Now uv become the horizontal and vertical coordinate, which are actually the azimuthal coordinate u and the axial coordinate v. And now we are saying axisymmetric means that there is no dependence on u. Okay? And the second thing is that the only metric change is due to the shear. So it's due to the fact that this line that was long 1 becomes long 1 plus gamma square, where gamma is the tangent to this angle, and this is written here, and that the change of angle between the vertical and horizontal is due to gamma. The tangent of this angle is here, and this is the metric. Now, if you put this into Gauss theorem, this is what you get. It's very easy. It's very easy. It's just a differential equation in one variable, gamma, the shear, with only one type of derivative, the derivative with respect to the vertical axis, because we have assumed axisymmetric actuation. Okay, let's solve this equation, right? So we are here at the Newton Institute. We have to solve equations. So let's solve it in steps. So let me solve this equation first by looking for surfaces of zero Gaussian curvature. So I want this to be 0. And the easiest way to make this 0 is to make 0 here, the very inner argument. So if you make the shear constant along the axis of the cylinder, you get a surface with 0 Gaussian curvature. Which surface is that? Well, this is another bit of integration you have to do, but you can prove it. Well, it's cylinders. So this mechanism is the one that is this here. So it's not this one, okay? It's with sliding, but it's uniform sliding, and it produces cylinders from cylinders. Now there's a more interesting, the reason I did all this is because there is a more interesting way of making this a 0. It's modulating along the axis, but so that this product is independent of the vertical coordinate, right? So I make this a 0, not by killing everything. I keep this alive, but I kill the derivative, the dependence on the axial coordinate of the product of these two. Okay? And these are cones. So these are the things you can do in this way. Right? So if you want to produce cones, you have to be able to modulate along the... Okay, now that you have learned this, we do more. So we solve the whole problem. So we try and find all the axisymmetric surfaces with constant Gaussian curvature. So we develop an atlas of this, and this is the atlas. Okay, so these are all the surfaces mapped in a phase plane in which we are parameterizing things by the constant Gaussian curvature, you see that you can get lots of things, right? So this is an example of the one I was producing with another mechanism with my hands. Okay, so you can do the same thing in the Euglena by shearing. And so in modern terms, we didn't use this language when we solved this problem. What we have done, I think it's useful, you know, I like to do these things, but I think it's useful. How are you doing the time?
We have maybe 7 minutes.
Okay. So let's remember, so we now use the terminology direct problem, inverse problem, right? So let's, I mean, direct problem, inverse problem comes from, at least in my field, terminology coming from solving elasticity problem or solving PDEs. Well, you solve a PDE, then you have a canonical PDE in which you have certain things that are data and certain things that are unknown. In elasticity, the data are geometry, material properties, loads. The unknowns are the resulting shapes. This is the direct problem. You solve for the displacement when all those things are coefficients and are assumed to be known. The inverse problem is when you assign the displacements, you measure the displacements, and you want to infer the material properties. Like in tomography, you measure the image, you want to infer the properties of the things that have diffracted light or X-rays and have produced that, right? So here, what is direct and what is inverse? Okay, it will be worth discussing this. In this case, the direct problem is to produce a certain Gaussian curvature. Right? I want to produce a surface with, so it's shape. The inverse problem is the shearing mechanism, because this is the rules of the game. We want to do Euglena, so Euglena can only shear the surface. And so it's the shearing mechanism that produces that pattern. Okay, so the direct problem is the atlas. For each Gaussian curvature for which the direct problem has a solution, you ask yourself, what is the pattern that produces that? And you have a formula to do that. Okay, so these are the formulas that give you, in a non-dimensional coordinate, along the axis, what are the shears that you have to apply. Very well. And now you apply all this to Euglena. Okay, so first let's apply this to Euglena in a conceptual way. So the key thing for what we were seeing, the peristaltic waves, was a bulge that moves along an axis. So I need a bulge, Gaussian curvature non-zero, a bulge, and I need a translationally invariant construction so that I can produce a peristaltic wave. Okay? So how do we do that? Well, we join a cylinder, which we can do, with a cone, which we can do, and we could do it discontinuous. But if we are, very ambitious, they want to do it continuous, then we take two joining surfaces from the spindles and from the bulges. And now we get a perfectly translationally invariant construction. We can move this bulge along the body. Okay, so this is Euglena right. And yeah, so this is in theory. Is it true? Yes, it's true. So this is the way Euglena moves. So these are the stripes that are sliding one next to each other. So this is the how. The shape control is produced by a variant of this mechanism by which the fibers slide. Okay? Now let me tell you something about the why. Okay? The why is complicated. And let me first say the answer, and then I illustrate it. So the answer is that the swimming is the normal behavior. If I'm an Euglena free in space and alone, I swim. And then at some point I move around, and I swim by beating a flagellum that does something similar to my arm. And then something happens, right? So we try to make this quantitative. So we put an Euglena into a tapered capillary to explore whether what I just showed you was happening or not. So this is Euglena swimming happily. You will see the flagellum here. Now, at smaller diameters, it starts saying, well, I don't know, what should I do? At even smaller diameters, it's able to engineer a maneuver so that it can change direction. And at even smaller diameter, it starts crawling. So it's using the peristaltic wave that I told you to escape from this and go back, okay?
But Antonio, you showed us those shape changes without the restricted geometry.
Yes.
What did you do? Lopped off the filaments?
Yes. No. It still has filaments. It can lose them.
No, but you showed it without, you showed it doing these shape changes without the restricted geometry.
Yes.
So why was it doing it there?
Yes. So the key is in this picture, it's a similar story to the apple tree, but you need to know something about, so in order to do these things, we had to learn how to do microscopy ourselves. So we said, Euglena, no brain, it knows Gauss theorem. We thought that everybody would have just said, how beautiful, we want to see it. Nobody wanted to see it. The only way we had to do this was to learn to do microscopy ourselves. What is the most important thing we learn in optical microscopy? Is that it's 2D. So there is only one plane that you see. So if you are seeing this, it means that it's flat. So this is between two, right? Okay? Answer to your question?
Okay.
Yeah, so this is squashed between two surfaces. Very well. So, okay, this is the how and the why. I see. Yeah. So, okay. So this is the, the magazine part of the story, which has recently appeared. Now there's the tough part of the story is to do the modeling of this. And of course, I will not have time to do this. So if you want to go from magazine to understanding something quantitative, you have to model. So the question we asked ourselves was to study quantitatively the effect of confinement. There is one observation. Let me put these two observations, and I will close without telling you how we solved it. So we saw an effect of confinement, right? So immediately, what you understand is that in the absence of confinement, the speed is zero because the crawling speed is zero because it does not crawl. If you confine it too much, the speed is zero because it has no room to explore shape change. And so there must be an optimal velocity, okay? And so these are the speeds. This is the optimal velocity. It's obvious because the behavior lives in a confined window of opportunity, because if it's too confined or too little confined, it doesn't happen. The thing that was more surprising is that the speed of the peristaltic wave along the body was not affected by confinement. Okay? So we asked ourselves, can we understand that? In order to do that, we built a model, a quantitative model of this. So it's a shell that it's interacting with a capillary, with a fluid, already very complicated. On top of that, there is the fact that it's made of strips that can slide. If you add, so it's a motor clutch system. So if you add just passive sliding, only friction. So if you wanted to model a system like that, which is just passive, like this one, where you want to understand what is the diameter of the bulge corresponding to a certain shortening, you have to model the friction between the strips, right? And the friction between the strips can be modeled as a law like that, that there is a sliding speed that is zero if up to a certain yield value of the force, and then it goes, right? An active system, in which is not friction, but there are motors, is governed by things that are instead called the force-velocity relationship that appeared in Dan Needleman's talk in the behavior of motors and filaments. So, the motors make you run, but if you apply a force, the motors slow down, and there is typically a linear relationship. Okay, I mean, it was not linear, but a relationship like that, that tells you that there is a free speed in the absence of force, that there is a stalling force, there is an intermediate behavior, right? So we put all this, and we try to ask ourselves the question whether the model could explain the independence of the traveling bulge. And what we managed to show is that pattern of activation. These are pattern of activations in space-time along the body. This is along the body of the animal. This is time. So if you can explain these curves, so you can reproduce these curves with patterns of activations that are invariant with confinement. So the model was used to test this hypothesis that the motors are not reacting to the level of confinement. So the speed emerges out of the global properties, but not at the fact that the system changes the speed of activation. Okay, so this was the outcome of the model. With this, this is references, and let me go to the final slide. So the goal of this is, in a sense, to explore similar ideas that were presented in the previous talk about learning from nature how to engineer new systems. One of the interesting things is this behavior due to motors. Motors in these systems are distributed. There's not one motor, there's millions of motors. This is something that is not very much explored in engineering. Another one is self-organization of the mechanical response, but I don't have time to talk about this. Thank you very much for your attention.
Can we have Henry set up while we take some questions? Oh, first.
So I see in your picture there are dislocations in the pattern.
Yeah.
Does that play a role?
What's the? I know. What's the question? Is it?
I see dislocation
Yes,
in the
yes,
pattern of those lines.
yes.
Does that play a role in the control process?
Not in our control process. We had to ignore it, but it's a very good point. And in fact, you know, there are two singularities in this animal. One is a hole, which is where the flagellum emerges. One is at the tip, and they are resolved in two different ways, with a hole and with dislocations there. It's a fascinating observation. We have done it ourselves, but there's little more I can do, I can say, besides this.
So when
Yes.
you know, when the flagella hits the wall and so on, then it starts swimming only by the motors inside that are doing these changes, or the flagella is not important?
I couldn't hear you. Could you please shout?
When the flagella is not important in the motion, you show it that when it starts hitting the wall, then you start developing these motors.
No, I was speculating without knowing it as a fact that there is no sensor, proximity sensor. So the flagellum is the propulsive organism, but it's also the sensor for confinement. So confinement affects the internal working of the flagellum. Something happens. There is a signal that says motors stop being active in the flagellum, start being active in the body. So this is totally speculation, okay? But this is my speculation.
Okay, well, let's thank Antonio again.